Okay, your notes today are on limits. Limits, right here, this is how you would write a limit, and you read this math sentence like this. The limit of f of x as x approaches a equals L. We've spoken about limits before when we talked about end behavior. When we talk about end behavior, we're talking about as x approaches infinity, because x can't actually get to infinity, and it's the same thing here. If I speak about the limit on this graph, I can talk about what's the y value as I get closer to a certain x value, and it's really just that number on the graph. But sometimes, even if a value is not defined on your graph, if you were to have a hole there, you can still talk about the limit as you get really close to that value. So that's what we're talking about here. Limits are really the starting point for calculus, because when you talk about calculus, one of the things that you might do is find the area underneath a curve. Like I might find the area underneath this curve. And you're going to find the area of rectangles under the curve. This happens next year. But you're going to basically break it up into rectangles like this. And then you're going to find the limit as your rectangles get infinitely skinny. So if you think about this, obviously there's a little bit of error in your rectangles if you're just trying to calculate the area of these rectangles. But if you can make them infinitely skinny, then you could actually find the area under the curve. So limits are going to be essential for calculus next year. When we talk about limits, we're also going to talk about continuity. So for continuity, we talk about whether or not a function is continuous. In the past, we said it's continuous if you could draw it without picking up your pencil. But this three-part definition is much more mathematically correct. First of all, the function has to be defined at that value, so you don't want to have a hole or an asymptote. And the limit has to exist. So that's going to be this part here. We'll put that together. And then lastly, the limit has to be the same as the defined value. So sometimes when the limit's not the same as the defined value, I'm just going to show you really quick, and as we do more examples, it becomes more concrete. But if I see a function like this one, what happens is my limit is the number I'm getting close to as I approach 2. So that's this number, even though it's a hole. So my limit as x approaches 2 is 3, but f of 2 is 5. They're different values. And so if your limit is not the same as your defined value, then you say that the function is not continuous. So again, another definition that will become more concrete when we look at examples. And when you determine a limit, this limit is going to equal some value L if the left-hand limit and the right-hand limit both equal L. So here it says, note we use the plus sign to indicate approaching from the right and the minus to indicate approaching from the left. So if I want to approach a value like 2, I could approach it from the left or I could approach it from the right. So that's what these values mean. So right here, this is from the left and this is from the right. So that doesn't make the number negative. It's just talking about from the left or from the right. All right, so let's look at our examples. We want the limit as x approaches -5. The negative's in front of the number, so that's the same -5 you've seen your whole life. -5 is right here on the function. So we're going to approach -5 from the left and from the right. And when we do that, what y value are we approaching? What's the number?
4.
4, yeah. So as you approach -5 from the left and from the right, you're approaching a y value of 4. Okay, for B, we talked about this one already. As x approaches 2, it does not matter that there's a dot up here. That dot's all by itself. As you approach 2 from the left and from the right, you're approaching this value where the hole is. It's fine that there's a hole there. That's not a problem for a limit. So that value would be 3. Okay, that's different from another question, like what if I added question f over here? What is f of 2? Okay, f of 2 is the filled in value, which is how much? 3 is the limit. Remember, that's the one that you're getting close to, and there's a hole there. But see that colored dot right there? That's what f of 2 actually is. So if 2 is my input, then 5 is my output. Okay? So limit, define value. They're different. All right, the limit of f of x as x approaches 0. So we have to approach 0 from the left and from the right. So here's 0. So I'm going to go left and right, and I'm going to approach. And what y value am I approaching? Is it the same number? No, it's not the same number. So if you're not approaching the same number from the left as you are from the right, then you get to say the limit does not exist. So that's this one. The shorthand for does not exist is DNE. You can write does not exist or you can write DNE. Do not write undefined. Do not write no answer. Don't write anything else. You have to write does not exist. All right, I want you guys to try the limit of f of x as x approaches 4. So take a minute, find 4, and then put your fingers on the left and on the right and see what y value you're approaching. Okay, what's the answer? 0, very good. Okay, and then E says, is f of x continuous at 2?
Hi. Oh, sorry.
Okay, we're back. So continuous, we have to look at the 3-part definition. So first of all, is f of 2 defined? Okay? F of 2, is it defined? Yes or no? It was over here, right? We said f of 2 is 5. So if f of 2 is defined, give yourself a check. Does the limit as x approaches 2 exist? We found it, right? The limit was 3, so that is a check. And are they the same? Does f of 2 equal the limit as x approaches 2? Are they the same number? No, this one's 3 and this one's 5. So if it fails any part of the 3-part test, then you say it's not continuous. Sorry. Not continuous. Yeah, if you guys can't see, then it's not on the video, so make sure you let me know. All right, number 2, given the graph of y equals absolute value x over x, what is the limit as x approaches 0? So look at that graph, approach from the left and the right, and then I want you to write down your answer. Okay, what did you write? Yep. The limit does not exist. Okay? All right, I'm going to let you do most of number 3 on your own. I just want to go over that terminology there real quick with the minus and the plus. In 3a, it says the limit as x approaches 2 from the left. So if you have a left-hand limit, it doesn't really matter what's on the right. The left and right don't have to match. So here's 2, and then you want to go to the left of 2. So I'm at the left of 2 now. I'm going to go back and approach 2. I'm approaching what y value? 3. It's fine that there's a hole. It's fine that the right-hand limit doesn't match it because we're just doing a left-hand limit, okay? So this answer's 3. I'm going to pause the video and let you guys work on that for just a minute. Okay, so we're back. We're going to go limit as x approaches 2 from the right. So as you approach 2 from the right, what y value did you get close to? 1. And then the limit as x approaches 2, it has to be the same from the left and from the right. But we got different numbers, so what do we write? DNE does not exist. Okay. The limit as x approaches 5 from the left. So 5 is over here. and we're going to approach 5 from the left. So here's 5. This is the left of 5, so I'm going to approach it. What y value was I getting close to? 2, right? So ignore that dot down there. That's only if I asked you f of 5. And the limit as I approach 5 from the right is also 2. It's okay that there's a hole there. And so because these are the same number, the limit as x approaches 5 is going to be what? 2, yeah. All right, and then it asks me about whether this graph is continuous at different values. And the last one, -3, that one's not clear unless I know whether this graph is going to continue or if this is an endpoint. So I'm going to make that decision. I'm going to decide that it continues. If -3 was an endpoint, the graph would not be continuous there at the endpoint because you have to be able to find the limit from the left and from the right. But in this case, draw the arrow so that your graph continues, and then we'll be able to find all of these. So is the graph continuous at 2? Okay, it's not continuous at 2 because of what part of the definition? 1, 2, or 3? So part 1, f of a is not defined. That's true. Does the limit exist? The limit also doesn't exist. So at 2, it's no. And it's because f of 2 is not defined. And the limit does not exist. You need to be able to explain your answers. Okay, is the function continuous at 5? Okay, so here's, oh, I need to put it on the screen. Here's 5. Does the limit, oh, so the first one is f of 5 defined? Yeah. It's defined, it's the value here, 1. Does the limit exist? Yeah. Yep. Are they the same value? No. So even though they're both defined, I would say f of 5 does not equal the limit of f of x as x approaches 5. And then is it continuous at -3? What do you guys think about -3? Yeah, now it's fine because we showed that it continued on. It's defined. I can see the value 0. The limit also equals 0. And because they're the same number, we can say that this is continuous. Okay, what questions do you have on page 1? All right, turn the page. Okay, infinite limits. An infinite limit is really just a special case of undefined. I'm sorry, it's a special case of does not exist. So if you have a limit where they both go to infinity, so here the limit as x approaches 0, they're both going to go to infinity. We can say that this answer is infinity, but technically it does not exist. So the best answer is infinity, but you have to understand that that's a special case of does not exist. So let me move this down. Special case of DNE. Okay, this graph right here, let's just sketch a quick graph. Do you guys remember how to find your vertical asymptote? Is that your denominator equal to 0? You get x equals 3. And how about your horizontal asymptote? The degree on the top is the same as the degree on the bottom, so you take what ratio? Bless you. The coefficient, so 1 over 1. So you have y equals 1. And you're going to have an up branch and a down branch. So let's see. Okay, so just a quick sketch without any numbers I have here and here. So the limit as x approaches 3, as I approach 3 from the left and from the right, am I approaching the same value? Okay, this branch is going to negative infinity. Where's this branch going to? positive infinity, so they're not the same. So this one we're going to say is does not exist. It's not a special kind of does not exist, it's just the plain old does not exist, okay? So this one's does not exist. This is infinity, which is a special kind of does not exist. All right, this one, number 6, is an interesting case, and I'm going to actually pause the video for a minute to pull up my calculator, and if you guys have a graphing calculator, you might want to look at this one too, because this function is so interesting. You want to graph it on your calculator. I have it graphed right here. It looks a little bit like what's on your paper, but you're going to want to zoom in to see a little bit better. So I just click zoom in and enter. And now it's going to look a little bit more like what's on your paper, right? All right. Now this is called oscillation. It's different from normal sine oscillation. I'll explain why in just a minute, but I want to show you what happens when you zoom into this graph. Normally, if you zoom into like a normal sine graph, think of a normal sine graph. If you zoom in close enough, this part right here in the middle is going to look like a line, right? When you zoom in close enough, it becomes more and more linear looking. But look at what happens when you zoom in on this graph. It actually becomes more and more crazy. It doesn't become more and more like a line. So zoom in again. Zoom in. Enter. All right, do you see how when you zoom in, it's getting wilder and wilder? It's not getting more and more linear. And you can zoom in again. It's an interesting function because we have never seen one like this before. Okay, so this is what oscillation means. Oscillation means as you approach a value, instead of becoming more and more linear, it's becoming more and more wild. Okay? So for number 6, it's going to be does not exist because of oscillation. All right, do not confuse that word. There are other words that sound like oscillation that are not oscillation. That's the right word. All right, so the limit of a function does not exist if the left limit doesn't equal the right limit. And it also doesn't exist if we have this crazy oscillation. This is really, though, a function where we see it the most, sine 1 over x. And lastly, the limit does not exist if it's that very special kind, which is infinity or negative infinity. All right, so we can also determine if the limit exists either by sketching a quick graph or by looking at the information to evaluate the left and right limit. So let's look at number 7. Number 7 actually looks a lot like a problem from the front. What did we see in the front with the absolute value? It was this one right here. The absolute value is on the top here, but really it doesn't matter if the absolute value is on the top or on the bottom. So what we're going to do is try to figure out what kind of transformations we have going on here. This is x minus 3. If I want to make this x minus 3, what could I factor out? Negative 1. So if I factor out negative 1, then this becomes x minus 3 on the top. And then on the bottom, you have absolute value of x minus 3. So if the graph I had before was like this, with transformations, it's going to shift left or right? It's going to shift right 3, yeah, because remember the x's happen inversely. So 1, 2, 3. So my holes are going to be here and here.
Is it just one absolute value?
Oh yeah, sorry, that doesn't make sense, does it? Here you go. Okay, so the holes are going to be here and here because we shifted them right 3. But the other thing that happens, this negative is going to flip the graph, so it's going to be like this. So this branch comes down here. And then this branch comes up here. Okay? So now that we can see this, we can look at the limit as x approaches 3 from the left. As x approaches 3 from the left, what y value are we getting close to? 1, yeah. And remember, because it's a left-hand limit, we don't care about the right hand. So this is just 1. All right, in problem 8, we want the limit as x approaches 2. So we need the left limit and we need the right limit. But we don't actually need to know what f of 2 is. So looking at the 3 parts here, which piece do we not care about? 1, 2, or 3? 2, right. This is our left limit. This is our right limit. But we don't need this one right here. That's what we would need if we wanted to find out f of 2. We don't need that. So what we want to do is figure out if our left limit equals our right limit. So we're going to plug in 2. We're going to plug it into this x and to this x to see if we get the same value. So from the left, the limit as x approaches 2 from the left. Let's see, I put 2 here, so I have 3 times 2 plus 1. What do I get? 7. And the limit as x approaches 2 from the right, this one, 2 squared plus 3, what's that? Okay, so then I can say that the limit as x approaches 2 is what? 7, because the left and the right are the same. All right, so you've done the hardest part. The next 2 pages are all about substitution. Sometimes when the values are defined, to find the limit, all you have to do is substitute the number in, and that's what we're going to be doing. The rules at the top of page 3, they just tell you that you can do all of the things that it seems like you should be able to do. Remember with logarithms, a lot of you guys tried to create rules that didn't really work. In this case, in limits, all the rules that seem like they should work, they actually work. So if you have the limit of a product, it equals the product of the limits. If you have the limit of a sum, it equals the sum of the limits. You can break things down as much as you need to. I'm going to do a couple of these with you, and then I'm going to give you some time to work on them. Okay, so these are your rules right here. And the first one says if you have a constant, the limit as x approaches c, if this is some value k, it's going to equal k. Now that might sound confusing, but let's look at the specific example for it down here. The limit of the function 3, so that's y equals 3. Think about y equals 3. 1, 2, 3. Y is always going to equal 3. So as x approaches 1, what's your y value going to be? 3. Yeah, it's always 3. Okay? So that's what that constant rule is telling you right there. Okay, the next one, the limit as x approaches negative 4. So you're going to put negative 4 in for the x. What do you get? It's just negative 4. Okay, see how I just substituted it in for the x? Sometimes the easiest problems are the most confusing. All right, number 11, you're going to substitute 1 in for the x. So we're going to have 4 times 1 squared plus 3. What do we get? 7, yeah. Okay? So these problems are all done by substitution. When you get to number 14, you might need to remember a little bit of trig. And actually, at the end of class today, we're going to go over a few trig problems. But I want you guys to keep working on these. I'm going to pause the video. All right, number 12, we're going to plug in 1, 2 times 1. What? Oh, thank you. Unfreeze. Okay. What do we get? 1 over negative 1, is that right? So you guys got negative 1? Square root of 0 plus 4 is 2? You guys remember what cosine 0 is? Yeah, cosine of 0 is 1, and then you multiply it by 0 and you get 0. Yep.
For number 13, would it be positive, negative?
That's a good question. A lot of people want to do that. If I had an equation like x squared equals 4, when you solve that with a square root, you get plus or minus 2. But if you have a square root to start with, then it's just positive 2. Okay. All right, next one, plug in a half. So you have 5 times a half plus 7. 9.5 or 19 over 2?
You might want to maximize the screen.
Maximize
It's
it?
kind of like a little window.
Oh, is that okay though? Because I think it's better for seeing this way.
Fine.
Okay. I like it this way, but let me know if you can't, if there's something you can't see, okay?
Okay.
All right, and then 3 times 1, 1 minus 3. 3 over negative 2, yeah? So negative 1.5.
It's 4.
Oh, where's it 4? Oh, it's a 4. Then I did it completely wrong. Thanks for telling me. Mhm. So we get 12? You sure? Okay. All right. Number 17 is a constant function. Don't be confused by the fact that the constant is e. Okay, so it's going to go straight across at about 2.7. And so no matter what your x value is, your y is always going to be at what value? E, good. All right, turn the page. When you turn the page, they tell you the limit as x approaches c of f of x and the limit as x approaches c of g of x. So they're just asking you to put this information together. How many people are done with the last page? Okay, that looks like 0, so I'm going to give you a couple more minutes to work on the last page. I'll show you for one example how you still are just substituting in directly. All right, so I have a square root of 2. Oh, thank you. And then for f of x, I'm going to put in 2 minus 4 and put in the negative 3, and then I'm going to evaluate that. Okay, so you see how you're still just substituting in? So I'm going to stop for a minute and let you guys work on that. All right, number 19, we're going to plug in 2. 2 plus 1 to the 3, what did you guys get? 27. All right, this one I have 2 times 2 plus 3 times 3. Oh, negative 3, right? And then negative 3 minus 2. So I have 4 plus negative 9 is negative 5. Is this one just 1? That's right? Okay. F of x is 2 times 2 times negative 3. What do you get? Negative 12. All right, so I have 2 times 0. What do you get?
0.
Yep. 2 squared, 1 minus negative 3. What's this answer?
We can't see it.
Thank you. All right, did you guys get 1 for that one? Okay, so I'm going to stop this video. I'm just going to give you a couple trig review problems after that, okay? You can do this on the back.